right, we'll get started. Welcome to the College of Architecture and Design at Lawrence Technological University, and welcome to those joining online. I know we've got a cohort joining us. We're also streaming on YouTube. My name is Carl Dobman, and I'm the Dean of the College. We take a broad approach to design. We do this because we offer a range of design degrees that include graphic design, product design, transportation design, game design, interiors, and architecture. We believe that the future of design is multidisciplinary and technological. Our Design and Technology lecture series allows us to engage in a design discussion and offer broad perspectives on where we think we're collectively and professionally heading. A little bit of housekeeping to start. I want to introduce an upcoming lecture. We have our Distinguished Architecture Alumni Lecture this Thursday evening. It's the 26th year that this has been running, and we'll be honoring Amy Baker, principal of Amy Baker Architects. And you can also see past lectures on our YouTube page. I'm very excited now to introduce Paul Lewis, today's speaker in our Fall 2023 Design and Technology Lecture Series. Paul Lewis, FAIA, is a principal at LTL Architects, Lewis Cermaki Lewis Architects, based in New York City. He's a professor at Princeton University. LTL is focused on plant-based building materials and the creative repurposing of buildings as they've completed academic, cultural, institutional, adaptive reuse projects throughout the United States. LTL are the 2019 New York State AIA Firm of the Year. They've received National Design Award. They've been inducted into the ID Hall of Fame and many, 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 many other awards, a lot of awards. LTL Architects are the authors of Intensities from 2013, Opportunistic Architecture 2008, and Situation Normal Pamphlet Architecture number 21 from 1998. LTL's early work occurred at a very interesting moment in time with the rise of digital design and fabrication. They carried out a number of amazing small interior projects in New York City. Their drawings of these projects highlighted the potential of representation. I also say this because I know that there's a number of students in our VisCom class attending today. But their drawings of these projects, some of which you've probably seen, I hope you've seen, highlight the potential of representation as well as hybrid drawings that are both digital and hand-drawn. Their practice is nimble, critical, and straddles the profession and academia. And even if you follow their work, you'll see the way that they position themselves and the types of work that they do is constantly evolving. Their 2016 book entitled Manual of Section has been translated into 7 languages. Their follow-up book, Manual of Biogenic House Sections, reveals the architectural potential of plant and earth-based materials. It was released at the end of 2022. Paul is the past president of the Architecture League of New York and still serves on the board, and he's a fellow of the American Academy in Rome. He received a BA from Wesleyan University and an MArch from Princeton University. It's a great pleasure to have Paul with us in person today. We're also comparing notes when he arrived this morning, and we realized that he taught one of the critical practice years in 2005. So it's been a while since he's been here. It's exciting to have him back. He's also going to be our guest at the Affleck House. So if students are interested in attending dinner tonight with Paul, please talk to Sarah, and she'll coordinate first come, first serve in terms of being able to attend that. We can accommodate about 10 students. At the end of the lecture today, I'll be running around with the mic, and we have about 15 minutes for Q&A. So you might think about some questions during the lecture. So please help me in welcoming Paul Lewis.
Thank you, Carl. It's a great pleasure to be here. And I think the introduction did a fantastic job on setting up what I'm going to present today. As Carl mentioned, we published this book in 2016, And really the argument for this was to try to position section as being kind of a site of invention, a site of speculation, even though a section is arguably something that witnesses something that's unseen or invisible, the vertical cut through a building. It's where a lot of performance takes place, meaning structural performance, environmental performance, et cetera. And the book has been super successful. It has been translated into 7 languages. We've yet to see a copy of the Turkish edition, so if you have a copy, please let me know. But I will argue that, that in some respects, that this new manual that we produced, we think is actually in some ways more important. It's been an interesting time for us in our practice to kind of rethink what we're doing, rethink the material basis of buildings in light of the kind of crisis of climate, and in some ways imagine a different paradigm for architecture. So we're both excited about this and where it might go. The basis of the book is really looking at 9 kind of dominant plant and earth-based materials, and then a final chapter in reuse. And reuse has been always present within our practice. As Carl mentioned, it's something that we've always been super interested in. You know, the cliche is the most green building is the one that already exists. We know that, but it allows you to do other things, right? It allows you to kind of rework existing structures that are not meant for the purpose that you're now adapting them for, whether in this case it was a theater that had been turned into a department store that then we figured out a way to turn it into a contemporary art center. So there are kind of really interesting possibilities that might come from these kind of inventions, looking at ways to kind of reimagine the storefront from the 1950s department store and kind of reimagine it as a site of contemporary art, thinking about kind of tactical uses of staircase and vertical circulation to get you up into to the main gallery, looking at ways to kind of modify and accentuate the really almost the kind of friction between what exists and when you're adding new. And in this particular project, we were actually able to repurpose the building that we'd already repurposed by modifying it about 5 years after we had initially completed it, adding the rooftop top deck, and then thinking about how these kind of urban buildings can have impacts back out to the street itself. Or in this particular project was an administrative headquarters for Claremont University Consortium. And what was great here is that we were working with what used to be the maintenance building on campus. You don't get to do mostly column-free, 100-foot wide, 35-foot high ceilings in a 1-story office building. You just don't. But we were able to do it, looked at modifying it through bringing in light, had to do all the mechanical systems in the ceiling, developed a kind of custom baffle to basically shroud some of this infrastructure, and then that became the aesthetic of the entire project. In a sense, making an open office for 100 employees because of the unique nature of the existing building. Or in a different adaptive reuse project, here we were looking at a pier in Coney Island, which had been destroyed in Hurricane Sandy, Superstorm Sandy, and looking at small details, like how could a bench both allow you to sit with someone who wanted to look out to the water where you might have wanted to look at people, so you could kind of have a kind of bench that looks in 2 different directions, or a collective chaise lounge for sunbathing, and even looking at ways that a sunshade device could actually imprint through shadows the name of Coney Island onto the surface of the boardwalk. And a more recent project for Poster House. This is a through block kind of space between 23rd and 24th Street. And we had to imagine this as a site for a museum of the poster. We knew that that would require museum quality kind of controls in terms of humidity. So how do we find a way that we could both let the pass-through, which was super interesting about this building or this space, and have this kind of shielded acoustically and mechanically treated gallery space within it, a kind of nested volume, if you will, various sketches and what that might be, and ultimately looking at ways that you can kind of strategize the relationship between a very simple series of lines so that these intersecting lines would actually kind of focus on the door that would lead in from this promenade space into the gallery itself. We really then developed the project as one part of it was this about 220-foot long piece of millwork. I will say that 24th Street is about 2 feet higher than 23rd Street. So and the floor slopes the entire way. There's nothing level in it. It was a bit of a challenge. But what we liked is the ability to keep the street. The site of posters is originally the street, so we wanted to have a street within a museum for posters. But we got this interesting friction between the older shell and then the new shell, which you see on the right, this kind of split screen effect that you would get between those two. And then looking at kind of healthy building materials, on the right is basically a kind of clay surface, and on the left, most of the millwork was done with white oak. And then the gallery itself is more conventional, but throughout the project, we were looking for these negotiations between the new pieces that we would put in and then the kind of residual historical components here, the cast iron columns, and illuminating the Capitol, but also hiding it at the same time. Again, with a lot of this adaptive reuse work, the interest has been questions of operational carbon, right? So we've been attentive to solar angles and performance and insulation, and we've not been as attentive to questions of embodied carbon. I think this is something that the profession as a whole has not focused on, and it's really something that we've shifted our practice to attend to. So let me set the stage. What we're going to do for the rest of the talk is really combine these two different books and the content of these books. One is Manual of Biogenic House Sections, and then a book or a kind of pamphlet that we did that developed 5 specific houses that use plant-based materials as a catalyst for their architectural form. But just to back up, and this may be well known to you, this is not an argument that we're making, it's an argument that Architecture 2030 or the Carbon Leadership Forum or a number of organizations have made. But the short version, for those of you who have been living under a rock for the last couple of years, is that we are not in great shape with the climate. And in particular, we're going to have to find a way that our policies get us to about a 65% reduction in 7 years, increasingly more dire and difficult to get to in order to get to net zero by 2050. We know that buildings account for 39%. You've seen these stats before. If you haven't, you should have. And then Operation Carbon, which has been the focus, the heat, the energy that goes into keeping a building going, has been a larger chunk of that, but that's where most of the energy has gone. Embodied carbon, which is basically the amount of energy necessary to build the building, the upfront carbon, the material, all of the kind of energy that goes into making the building itself, is only 11%. The difficulty is that if you map this out of carbon emissions within the kind of building world between now and 2050, about half of it is actually embodied carbon, right? So we're attending to only half of the problem. And then you also have the added difficulty that the more higher performance you make the building, in a sense, the more efficient it is, the higher percentage of that ratio goes to the embodied carbon. So actually, as we make better and better high performance building, often with greater insulation, greater glass and steel, et cetera, we end up with buildings that the payoff time to get the return on that embodied carbon investment takes 30 years, right? And so that's one of the tricky things we're dealing with. So the other issue is, as much as we love reuse, we're not going to be able to reuse our way into the future because there's just not enough building stock out there. There's the demand for something like 2.5 trillion square feet of buildings by 2060. So the question then becomes, how do we rethink the legacy of modernism? Modernism, defined largely by concrete, glass, and steel, is highly dependent upon a huge consumption of fossil fuels. It tends to be linear and extractive. It assumes a kind of global deployment of materials, and the question of the environmental and health impacts have taken a secondary status to cost and, frankly, getting stuff done. And also, weirdly, architects just become consumers in this, right? We specify products, right? And so instead, I think there's an optimism about a possible biogenic and kind of geogenic future where we're working with plant and earth-based materials. We're working with kind of low carbon, if not carbon sequestering materials, thinking about the whole life cycle of those materials, trying to work local as much as possible, and also getting the benefit of not only decreased carbon, but also materials that themselves are healthy both in their sites of production and their sites of use. So you don't have the off-gassing that you have with petroleum and chemical-based products. We know that materials are not all equal, so this is the rough carbon consequence per meter cubed of materials, and it's super small to read, but maybe you'll see at the top is all the metals and glass. And then you start to get the sequestering line once you start to get into plant-based materials, woods, et cetera. And that's really the focus of the book, which is really to say, what are the materials that are currently being used that are plant-based materials or earth-based material? What are their life cycles? And how, more importantly, how have they been used to make innovative buildings? If we're not using architecture as a point of seduction, if we're simply reconstituting buildings from the 19th century, we're not going to get very far. Like, design doesn't have any agency if we're reconstituting models or building types that are just about a kind of return to some nostalgic past. So one of the questions, I'm sure you're going, well, why the hell are we doing houses? We shouldn't be doing houses, we should be doing housing. I completely agree. So the problem is that when we set out to do the book, we wanted to find examples of buildings that were built from these materials, and there are not a lot of housing or large-scale buildings that necessarily are built from these materials. So that was one factor. We wanted to draw buildings that already existed so we could prove and demonstrate that these can be done. The second thing is that houses are a site of experimentation, and that's going to continue. We also had the fact that the book is a small format, and when you draw sections of houses, you can see the tectonics, you can see what's in the wall. When you draw big buildings, you can't see that, so that had an alignment. We wanted to have a kind of typological consistency. And then the other thing we were really interested in is looking at ways to argue for smaller scale buildings, right? So yes, houses are a problem, but a house that's 5,000 square foot is much more of a problem than a house that is 500 or 800. Almost all the houses in the book are less than 1,000 square feet. So in a sense, the book is a critique of the current single-family home that exists in the States. In particular, that's ballooned from about 1,000 square feet in 1950 to about 2,500 square feet today. There's an added problem in that most of those materials, in order to build a house that big, most of the materials are cheap, and most of those materials are coming from petrochemicals with all their attendant toxicity. They end up in landfills. Go on at length about that, but basically it's a kind of a limited life cycle, a kind of take, make, and then dump process. The other thing that architecturally is kind of interesting and a bit of a difficulty is that we're really seeing houses and the kind of construction of the house as being basically a series of very, very thin layers. So in a sense, the sandwich is basically a collection of multiple cheap, lightweight, thin, single performing often. They don't often do multiple things. They do one thing legally. They tend to be argued for their hygienic quality, and they set up a clean distinction between inside and outside. This assumption that your wall is basically going to perform and protect you hygienically from the outside. And our interest in the book was to shift to things that were monolithic, things that were maybe more mono-material, heavy, perhaps, and then possibly also regenerative. And to think about that as a kind of different model for how one would organize thinking about the very architecture. So in a sense, whereas the manual section looked at the role of section to generate the buildings, and that was our interest, here we're looking at the combination of materials and also how they would produce through their tectonics, through their kind of inherent qualities, maybe, certain spatial consequences that were interesting. Throughout the book, we start each chapter with basically a kind of classification of the carbon per meter cubed. We then map out kind of where these things come from, what are their material paths from plant to construction, how do they get reused at the end of life or different cycles within this system. But also look more closely at what are the specifics of that plant, what are the basic steps by which you go from tree to different forms of lumber, and what are the dominant models in there. This is not meant to be exhaustive, but it's meant to give a sense of what these things, how we go from plant to building. And then each of the chapters has about 4 to 5 houses that we've documented through new exploded kind of axonometrics to show what the house looks like in plan and three-dimensionally. We have construction photographs on the lower left, exterior photo, interior photo, and most importantly then this cross-sectional perspective that we've drawn by modeling the house in detail, having an interesting exchange with the architects. Many of these houses are not iconic, and it was great to be able to work with 55 architects around the world to get them to kind of redline our drawings to make these as accurate as possible for the purposes of the book. As I mentioned, we've also, at the end of 4 years of working on this book, we wanted to design our own, like we kept going, all right, what will we design? So we designed 5 houses that look at combinations of different materials and how those could be a kind of source for invention. All right, so I'm going to go through a couple of these different chapters and kind of show some examples and show examples from our own work as well. All right, mass timber. This is, if you're a student, where you used to be asked, all right, well, what is your Rhino model made of? And you'd say, concrete. And now you go, CLT. So it's the default. It's becoming a default. And look, it's great. Mass timber is fantastic. It's the poster child for plant-based materials. It's a lot better than concrete and steel, but it does have its problems, right? What's great about it is that it's easily 10, 15 years ahead of where all the other plant-based materials are, right? So in terms of code, approvals, client acceptance, et cetera, fire, all that kind of stuff. So it places a path forward. But I think you probably know it takes a long time for a tree to grow, 30 to 100 years. Even with Forest Stewardship Council, you're often getting as much carbon loss by the destruction of the soil. Not oftentimes when a tree is, or a forest is harvested, you're only gonna be using maybe 50% of that tree. So it's a wash, right, at best. There are attempts to make that better with different models of mass plywood, et cetera. But it's not going to save us, right? Mass timber is great. It's not going to save us, and there's not enough trees in the world to do all the buildings with mass timber. Adhesives are a problem. So working with Dow laminated, things that don't require the adhesives. There are soy adhesives on the market, which are exciting, but trying to figure out where this goes next. Most mass timber is simply a replacement for the logic of post and beam, which is, I think, coming from other forms of construction. And we became really interested in architects that were using mass timber for its own qualities, the idea of a sheet good that is structural and can be milled. Jennifer Bonner's house Gables, a kind of fascinating house that is able to develop this complex roof gable system because of the specifics of the sheet good of CLT itself. In a sense, the house's whole geometry is based on multiplying these gables, and it would only really be possible at this level and scale and speed at which it was erected through the use of CLT. The project that we put on the cover of the book, Atelier Satama's Meteorite, is a really weird building. If you look at it closely, like, what's going on here? There are 2 layers of CLT. An inside layer and an outside layer. So that whole buffer space that you see in the section here is basically insulation. It's an air cavity and it's not filled. It's basically 2 skins. The entire building is 2 surfaces of CLT, and the outer surface has a stain on it, and that's it. So super fascinating. It gets rid of all those layers, and then it also sequesters about 48,000 tons of CO. 48,000 kilograms of CO2 equivalent. So, all right. So for a house we called the CLT A-frame, we kind of wanted to go in the other direction. Rather than milling CLT into all kinds of different parts, we were like, why don't we just use the entire sheet? Let's base a project on just taking the full blank, 10 feet wide, 50 feet high, and just setting them off in pairs. So at the back, you'd get 2 that would be stabilized by the kind of cross bracing of the stair. And then as they work their way to the front of the house, they just basically lean into each other. You get, at the top, you get this kind of crow's nest, this occupiable space that allows you to look out into the landscape. And then, of course, on the inside, the great thing about CLT is basically you don't have to use gypsum, GWB, gypsum drywall, and you get the finish of it. We also like the peculiar nature of this incredibly tall, almost 50-foot high ceiling, 1-story space. which took the A-frame and essentially moved it into a very, very different direction based on the logic of CLT. All right, bamboo. Bamboo needs a lot more different ways to use it. We're just starting to see different materials that are able to work with bamboo productively. But where CLT is limited by the slow speed of trees growing, bamboo is one of the fastest growing plants on the planet. It's super prolific, and it has a higher rate of carbon sequestration than wood. And I think you can grow something like 30 feet in 3 to 5 years, harvested not by clear cutting. You basically get rid of one culm among a group, so it's constantly regrowing itself because the rhizomatic root structure remains. It tends to be cut into smaller strips to be able to be glued together, so the question of the adhesive is one of the key issues. But you can also use the culm as a full structural component. Even though it has natural variation, it can provide kind of structural approaches and tethered together. So this house in Ecuador basically uses the bamboo as a structural frame. Interestingly enough, producing a kind of cross bracing that is also the circulation and the floor structure moving up through the house. It's kind of a fantastic kind of inhabitable incline plane moving through the domestic space. Or in Anna Herringer's housing prototype, you get a weave of bamboo forming a very unique, unprecedented external skin that then protects and provides a kind of protection against the initial impact of the elements, a light solar screen that then protects a little bit the rammed earth sleeping interior. But the skin would only be possible due to the flexibility, cheapness, and the strength of bamboo. All right, so earth. And there are people doing fantastic work with earth. It's exciting to see how it's starting to emerge in different forms. It's everywhere. It's one of the oldest building materials. Its thickness can work structurally, thermal mass. It can absorb and balance humidity. Typically, it's better if clay is the binder itself, and then your carbon emissions are quite low, particularly if it's acquired locally. Unfortunately, a lot of rammed earth that we know about is dependent on fairly high levels of Portland cement. So the question is to figure out a better, lower carbon binder, whether it's lime or just the clay itself. But it's great because it moves from a liquid to a solid state. And so you get this kind of interesting possibility of how do you, as a designer, work at those different stages. Is it with the block? Is it with the wall? Is it with 3D printing? So one particular house that we really liked, the Von House Fleury, this was really a combination of the earth loam with straw, a kind of cob wall. And it was just cut with a spade. And these are about 32 inches thick. But you get this fascinating kind of contrast between the roughness, if you will, of this spade cut, very thick wall, and then the timber ceiling and floor. The sandwich of the ceiling and the floor is then filled with straw, so it's also a straw house. As the insulation, you get the large overhangs that are going to protect the earth walls from the erosion from rain. So it's basically a single finish that's structure or cladding insulation and interior finish, although the structure is augmented by a series of 2x studs that you see located within the thickness of that wall. A different clay-based house worked with blocks, 15,000 blocks that were custom made on site, 4-inch by 8-inch by 16-inch by LTL Architecture, walls and also a vaulted ceiling, and then there's a very thin steel roof placed on top that protects the erosion but also helps harvest the water necessary. And I think at this point, one knows a lot about, you see a lot of 3D printing. There's not as much 3D printing with clay. I think there's some experiments being done in this building on it, so I'm excited by that. And I think this is super interesting. So a group out of Bologna, Italy, WASP, working with Mario, Cucinella Architects, 3D printed this house in, I think it was about 200 hours. There's the duration, about a half-inch layer over time. And it's as a test case, it was fascinating, in part because the walls were hollow and then filled with rice husks to form the insulation. And so the 3D printing allows you to have a kind of greater structural capacity with a reduced weight, and then be able to look at the walls as being insulation as well. All right. So we wanted to find a way that we could work with both bamboo and a kind of earth house by nesting one inside the other for this kind of new model of a farmhouse. And here we are looking at ways that we could produce an outside shell, kind of lamella structure, which is basically an interlocking of self-similar lengths of 8-foot bamboo with similar joints that would then be kind of assembled together in a kind of diagrid weave that allows us to develop relatively inexpensively and quickly a single spanning space. And then placed inside of that would be an earth-based house, largely excavated from the ground and also embedded in that ground, which is where the domestic space would occur. So you get basically a gradient of temperatures between the outside and the inside, this interesting play between what is a garden, what's a greenhouse, what's the actual house. And you also get this 30-foot by almost 300-foot long space that's quite large, efficiently done. The north side was clad in thatch for insulation, and the south had a plant-based polycarbonate to help facilitate the greenhouse performance. All right, so the last three materials that I'm going to go over are all ways to think about insulation. And I know everyone's, as soon as you say that word, everyone gets excited. It's insulation. Oh, it's the best. So how many semesters of insulation, do you study? All right, I ignored insulation for most of my career, right? It was just an R value, right? You just wanted an R value. You never saw it. It was in the wall as long as it was cheap, and that's all that mattered, right? Unfortunately, insulation is actually where a high percentage of carbon it has to be located. And most of the insulation products that are on the market now, and I'm thinking about it, spray insulation, XPS, EPS, bad fiberglass, et cetera, mineral wool. These are not only have high carbon emissions, but they're also often very toxic. If you've ever worked with bat fiberglass and you come away feeling bright and happy, you're not doing it right. It is awful. It's really nasty stuff to work with. And if you want to have some fun, just try taking a match to any XPS and see what happens. So it burns like you wouldn't believe. So there's trying to think about what are the possible replacements for insulation and what would that mean for the kind of the nature of the wall. So hemp. Hemp is pretty incredible, right? It grows quickly, about a foot per week. Reaches maturity in about 3 months. There's some places that you can get 2 growing cycles in a year. It has a long root system. It can actually help regenerate soils, grown with minimal water, fertilizer, and pesticides. In order to translate hemp into an insulation, you either work with the fiber itself and you kind of turn that into a bat insulation, or you separate the fiber from what's called the hurd on the inside and you shred the hurd, and then that combined with lime can form a kind of hemp lime. Inappropriately sometimes referred to as hempcrete. It's not a replacement for concrete. It's not structural. It's an insulation. It's the air cavities within the fiber that help make it be capable of resisting heat, thermal heat transfer. It can be kind of sprayed on site. It can be compacted on site. It can also be formed into blocks, packed into walls, prefabricated, et cetera. Hemp has a lot of possibility. One of the downsides to hemp is that you have to grow it in fields that might have been used for something else. And so there are some kind of displacements of agriculture that have come from hemp, but it has regenerative capacities as a plant. The second of the insulation is cork. Cork is amazing. It almost does everything, right? It can be structural. It's water resistant. It's thermal. It's antifungal. It has acoustic properties. If you like the smell of cork, it has great olfactory benefits, et cetera. And as I mentioned, it it can be structural. The downside to cork is there's only so much of it, and it takes a long time to grow. It's carved off the bark of a cork tree, tends to only grow in the Iberian Peninsula, so Portugal and Spain predominantly. And most of the cork used in architecture now is the excess of the wine bottle stopper industry. There are a couple of great examples. So this cork house is all cork. It's 1,268 CNC custom milled blocks that are then corbelled up to produce these kind of 5 roofs. The entire thing is cork, basically. It's a fantastic house. So again, the downside with cork is availability, duration it takes to make cork, and as a result, the expense, right? So, all right, so that leaves us 3, straw. And so the rest of the talk is, as Johnny knows, is all going to be about straw. So, all right. It's everywhere. Straw is everywhere. It's a waste product. It is not being used. Right now, the amount of carbon sequestered in straw around the world is estimated to be about the same as the carbon released in the making of concrete in any given year. So massive amount of, if one talks about carbon sequestering technology, it already kind of exists. It's there as straw. We just haven't harnessed or found a way to embed straw within building materials in a convincing and effective way. Most straw is left to decompose. It's not really used as much. Again, it's used as a kind of animal bedding, but most of it is left to decompose or burned. It's fast, it's cheap, it's plentiful, it's resistant to rot, and it actually can not only be an insulation material due to the air voids within the straw, but it can, if it's sufficiently compressed, it can be a load-bearing material. In fact, one of its early forms in Nebraska, the Nebraska wall assembly system is from over 120 years ago, is because you were working with straw bales. Those straw bales come compressed out of the machine at a sufficient level that it can be used as a building material. Typically, in this historically, typically what happens with straw is that it's stacked up as bales. It's a convenient form, and then plaster is added to the sides, about almost about an inch, if not more. And that plaster, whether it's clay or lime, really does form the resistance to fire, rot, moisture, insects, etc. And that plaster helps resist the vertical load. So in the California Building Code, where a straw bale is incorporated, it's because of the plaster that it's able to work. That's not the only way. You can embed straw within an existing stud wall, where it's basically just an insulation, or it can be formed into prefabricated panels, whether those are 2x panels or cross-laminated timber. Thatch is slightly different. I won't talk about it too much. One of the most interesting examples that we came across was Atelier Schmidt's Gardas Pavilion, which uses jumbo bales. And these are really big bales. They're 30 inches, 50 inches by 100 inches. They're 650 pounds each. And the baling machine that produces them at a density that they actually are load-bearing, right? So you can corbel the ceiling out of these. There are rings of CLT at every four blocks to help stabilize it and tie them together laterally. But effectively, the load is carried not by the skins that are put on, but by the straw, and then they're clad on top with a metal cladding to protect the plaster. It's a super thick building. I think, and it sequesters about 84,000 kilograms of CO2 in this relatively small building. So we became super interested in straw and wanted to figure out a way that we could use this thickness not as a problem. I mean, we've been taught, I don't know, for the last 100 years that thin is better than thick, lightweight is better than heavy, et cetera, right? All the legacy of modernism, and as if it's just unquestioned. And the idea that somehow you could have a thick building that sequesters a huge amount of straw that is not that expensive as a material, that became kind of intriguing to us. So what happens if we started to combine straw as a solid and thought about it as something you remove items from rather than building through addition, but design through subtraction, and combine a kind of void within in a dense thicket of straw. You combine those with voids of cross-laminated timber. So in a sense, this house is based on placing a series of cross-laminated timber, four-sided, relatively small rooms that are then positioned into voids within this otherwise kind of donut solid donut of straw. So the CLT basically is stitched together, so it helps stiffen the straw, and the straw helps stabilize the CLT and position the CLT. There's a central skylight, large overhangs to protect the clay plaster on the straw, and then the central skylight brings light down to the middle, and you essentially get this sequence of rooms that are carved up through the thickness of the straw. So in a sense, it's a kind of a Losian space that's wrapped around the inside of this really relatively small house. You go from the door all the way up to the roof terrace walking from room to room, if you will. And we really like the idea that the window, the space, the CLT room, and in a sense, the apertures and the voids within the straw are all one and the same thing, right? So hierarchies between different parts of the architecture start to get reworked in different ways. So the other mass straw, or the other straw house we looked at combined two different strategies for working with straw. One was a set of walls that would be running basically a kind of corbelled wall that would run kind of perpendicular to the contours of this hill, and the other was this thickness or this podium of straw that was carved in a way that's a little bit more similar to the last project we were showing you. These two masses of straw would then be tied together through roof box beams that were then infilled with straw, and had a kind of roof is basically clad in clay plaster, and then another layer of straw, unprotected straw, on top of a series of hemp fiber panels. And we like the idea that that top layer would actually decompose. You often get we get the question, aren't animals going to eat this? And we're like, yeah, they don't eat straw because it's not hay. Hay is a vegetable, straw is not. But nonetheless, if they wanted to, that's fine. We'll let them eat the roof, or burrow their way into the roof. And we like the idea that the building would blend itself back into the landscape. But then you get this interesting dynamic between the collective space for the house, which is more like this terraced landscape between these two straw figures, and then the private bedrooms and bathrooms that are carved back in with skylights, really quiet. And can you imagine, and I think it's probably the New Yorker in us wanting to get away from noise, that these would be incredibly quiet rooms. And we really like the fact that in this section, there's almost as much mass and straw as there is space. It's all on screw piles, reducing footprints by getting rid of as much concrete as possible. So anyway, so these were experiments trying to figure out how we could imagine an architectural set of inventions that are coming from the material, not just using those materials as a replacement for existing high carbon materials, which we thought was really important. So, all right. So this summer, we've been working on a couple of different experiments with straw that are continuing to the fall. So this is stuff that's very much in process, and it takes two parts. One is we've been looking at the jumbo bale in the form of these round jumbo bales, which can be very highly compacted, like 140 kilograms per meter cubed and up. So they have the ability to be both load-bearing and insulation, and that's really the kind of the holy grail that we're looking at here, is can we actually get load-bearing insulation? And so the other thing is, once you do that, you start to get into very different spatial qualities, like the ability to carve, these kind of thicknesses that are possible. We just like the idea that all of a sudden the design language starts to shift. These things are neither columns or walls, they're somewhere between. They can be fields, they can be figures, they can be rigorous or random. And then when you start stacking them up, you start to get architecture. So we had done a early childhood education, basically a preschool, for lack of a better word, a few years ago. This was in Bentonville, about 240 children from the age of very young to age 5. They were organized around playscapes that were appropriate for their ages. So you had a series of classrooms that then work out to the play spaces outside. There was this interstitial space where they could go out but still be within the confines. So if it rained, the kids could still get outside. And then all the rooms would link out to that. This was all done with healthy building materials. There was no plastics, no latex paint. We used mineral-based paints. There were no plastic toys. Everything was not just low VOC, but no VOC. But we were working with common building materials. We were working with steel studs. We were working with drywall, and that was frustrating. So our question was, could we imagine this building type with these jumbo straw bales, working with LVLs as a ceiling structure, basically developing a reciprocal frame where you would have these things tie into each other, spanning off of these large-scale jumbo bales, in a sense producing a room with a skylight in the middle of it. And then those rooms could then be aggregated together using CLT prefabricated bathrooms between the different classrooms, and effectively getting the same or similar size school, but all made out of a single story stacking of 3 layers or 2 layers of the jumbo straw bales. Where you can see, actually, this was just being worked on by Kyle Reich in our office. We haven't quite photoshopped the lower right, so that's why there's no shadows there. So we're getting there, but this is from yesterday. We have another version of the school just working with straight bales, not the round bales, but that's also still in progress. All right, the last thing I want to show is, and again, bear with me, this is in progress. We've been trying to figure out how we could actually compress straw and then hold it through a binder to make it a load-bearing insulation. Most straw that is compressed into walls, whether it's EcoCocan or Afterwall or Croft. Croft is an organization kind of design build out of Maine who's doing super interesting work. But it's basically compressing the straw in as insulation within a stick framing, a double stud, basically, a double stud. And so the 2x play the structural role, and then the straw plays the insulation, which is a cleaner way to get through code. So we were interested, could we actually compress straw so it's dense enough that it could be load-bearing, and then bind it somehow without having to default to the frame, but find a way that we could get the straw to be, as I said, load-bearing. We have made this compression machine, and the compression machine is kind of fun. It allows us to basically take, is this thing working? So let's see if I can get the audio. So it's basically a way to try to pack straw to get to 120 kilograms per meter cubed, 140, we managed to get to 163. The problem is holding that tension has been difficult. We've done a number of different binders. Here's glue, just as an initial test. Mycelium was a disaster. I was actually thankful. I was like, there's another, mycelium is not gonna save us, but that's another issue. It's great, but problem with mycelium is when you compress it into straw, it only grows in the outer inch or two, and then middle remains basically kind of rotten. And that's part of one of the real problems is that if the binder is too encasing, it will basically keep everything in the middle from drying. So the difficulty is how do you get it to dry properly while holding that compression in it? A lot of these, when we pulled them out of the mold, they'd start to explode out. But mycelium was, you can see here, it didn't penetrate into the depth. We made these 8 by 8 by 16 inch blocks, not because the plan is to make blocks, but it was a testing module that seemed appropriate. The plan is to make prefabricated units full scale at the scale of a wall. It's not a block system, because then you have to regrout it, and you're just basically undermining the structural premise. So we developed, so these are these frames. We had to let them dry for about 4 to 6 weeks. But they did kind of work, and so we've managed to get to the point where we have a range of these different test blocks, wood glue, lime. There's a SIP model that's stitched together. Worked with earth, cement, just to see if that would work. Different versions of lime, and then the mycelium. And we're trying to work with a soy-based and even a kind of geopolymer. So that, again, this is in process. And then even just if we work with a stitch system, a structure, just using the skin, but holding that compression in, can we get that to work? we had to cut these blocks down even more in order to put them into a compression machine. So these are those blocks with 4-inch by 4-inch chunks taken out of them, which caused some problem because it re-released tension to run them through the bandsaw. But we did get some interesting kind of results from the compression system, which this is sped up about 15 times. And you see it doesn't deform at all to the outside, and it springs back. That's and the part of the problem is that the first 1 or 2 inches are because it's been re-released as tension, and we need to find a way to compress it. But it's a nonlinear relationship to force. It kept taking on more and more load, increasing amount of load, but it reached the kind of limit where it stopped the machine. It hit the safety factor of the machine. So we're kind of curious to see how we make better blocks that are more pre-compressed so they can take on greater load. We're also in the process of doing a series of R-value tests by setting up, if you ever had an Easy Bake Oven, this is our version of the Easy Bake Oven. It's a 60-watt light bulb inside, slots for about 6 of these blocks around the periphery. We measured the kind of thermal mass, how long did it take for the heat to work its way through. We also and not surprisingly, the thermal mass of the foam was the worst, and the thermal mass of the lime-based one was one of the better. And we now are working with more precise sensors that are embedded inside the straw at about 3 inches in, and getting our values that are commensurate with what we thought, which is somewhere between 2 and 4, R2 to R4 per inch, which seems appropriate. But the plan is to try to continue to develop this, and we never thought we'd be at this stage where we were kind of making straw to see if we can get there. But part of the interest is that, how do we kind of, we argue that the straw bale is to what the log cabin was. Like, it's not a great it's fine, but it's not a great architectural form. And there are other ways that we might be able to approach this. So we just felt that we had to kind of get our hands dirty and see where we could take it, and that's where we are. So, but just to conclude, we're worried, but we're sufficiently optimistic that there's a possible new way to move forward that is fundamentally different than the 20th century reliance on modernism, all of the expectations of modernisms, not only the material of modernism, but all of the kind of spatial assumptions that we've inherited. And there's some interesting, intriguing, and open-ended possibilities for the future. It's just that we have to do it really quickly. So thank you very much.
So we have some time for questions. Since I'm here, that's the other way.
Thanks for the lecture. It was great. Glad to have you back on campus. Is your research based in your practice or in your teaching, or both? And how do you balance that as a professional in both arenas?
It's both. The straw compression work was all being done at Princeton and the architecture lab, mostly because the facilities there are just larger to handle it, and they have all the testing, certainly the Instron compression testing machine, and the students who are working with me this summer on that and into the fall are current grad students who are being paid through the work study. But the rest of the work is being done through our office, and and the book was all done through the office. And one of the things that we're trying to do as much as possible is to have this define how we're approaching projects. So, and it's tricky. I mean, I will admit, I think we've lost projects because we've gone in and said, we're gonna work with plant-based materials. We're gonna count carbon. We're gonna be concerned about all those issues. And that's, CLT and wood is embraced and known with some familiarity. But there's risk involved with the other materials, and some of them are not approved by code now. So that's tricky. So.
Eventually, how long do you think the industry would take to adapt these materials or even to accept them?
I cannot answer that. It's a great question. That is a great question. Well, we have until 2030, so, no, seriously, I think that this is, one of the things that's super interesting is just to look at, one can be encouraged by, 3 or 4 years ago, there were very few truly plant-based materials on the market. Now you can point to Timber HP coming out with wood fiber insulation out of Maine, Hempatexture with bat and different forms of hemp-based insulation out of Montana and Idaho. These are, Croft out of Maine. There are a handful that are emerging. It just needs to happen a lot more quickly. The U.S. is definitely behind Northern Europe, in part because there are regulations demanding certain uses of and consideration for life cycle assessment. So it's going to involve top-down regulation that drives it's not going to come from the benefit of everyone's sense of humanity, which doesn't often get us very far. So, sorry, that was really cynical. I didn't mean to say that quite. So.
I've got a few questions while the rest of you prepare some other questions. I wanted to highlight just there was one sentence that you said where you said you shifted the practice to attend to these particular issues. And I think it's just a great thing, especially among a group of students where practice is maybe assumed to be this monolithic thing, right? It's something you do, but it's not necessarily something that can be designed. And I think what you've shown is throughout the course of your practice, you've changed your focus and you've been able to do that. And it's something that you've been in control of. And so I don't know if you want to speak more to that, but I felt it was necessary maybe to talk to this group to just understand that practice is something that you have control over, an agency with, and yeah, maybe.
Yeah, it's something we're struggling with, which is to say that there's certain things we can control in certain formats. So, for example, self-generated designs. There are no clients for these 5 houses, right? But that allows us to experiment with them. We would like to have clients, but so I think it's one of these things where we've had to shift in order to develop designs. We haven't been able to be reactive and wait for projects to come in. Certainly when projects have come in, we're pursuing them, and that's very exciting. But it is definitely a kind of shift in terms of how we have to approach the work we're doing, and does put us in slightly different position when we go after work, which we kind of see it as a kind of longer arc. We're not as big as we were, 5-6 years ago, but that's a kind of necessary reality of trying to figure out how we're going to work in a direction we think is ethically necessary, and frankly is much more interesting. I mean, from our earlier work, we always been interested in materials and assembly, and to then have this kind of argument that now allows you to push against the very things we inherited, that's great. So, it's not, it doesn't have to be lightweight and cheap. It could be heavy and cheap. That's where things get really conceptually invigorating. So.
I'll keep going because I think that's an interesting answer. Just imagining that probably for a decade you were answering the question, how does this work scale up?
Yeah.
Right. Thinking about the small projects that were in New York, and then you did scale up that work, and
right.
Now there's like you said, maybe an ethical concern related to this, an interest in terms of how you drive the practice as well as drive, I'd say, the profession with your practice,
right.
To where you're looking at small speculative houses
right.
as something in terms of an arc
right.
of your career and
right.
of your practice.
Right. No, it's not linear. And I think that's okay. So, yeah.
No, I made fun of someone the other day for doing this. I'll come back to you all the way over here, and I'll come to you first.
Because this area of research and development is changing so quickly and developing so quickly. What are some resources for those of us that want to follow and really keep up with what's happening in this industry? What are some good resources to focus in on or pay attention to or look into?
Yeah.
I'll say it so you don't have to.
Yeah.
Your book is a good one.
Yes.
Yeah. And again, I think one of the key things of the book is we tried to footnote everything we could, right? And so, but I would argue, Carbon Leadership Forum, Architecture 2030 are really good resources. I think I'm trying to think of really good databases that exist. I know that both of those two, and Rocky Mountain Institute is another one, and I'm sure as soon as the recording stops, I'll think of 5 others that I forgot to mention. But certainly start with those 3 as really good, and they're really think tanks that have been working through this for a long time, right? So we're absolutely indebted to the work that they do to kind of drive things forward and to in a sense use it as an opportunity to kind of rethink what we're doing within this discipline.
Section, the importance of that in delivering a message, thesis of the book, and how's that kind of constituted your view?
Yeah, I mean, this really, what ties the 2 books together is obviously the section, right? And so that's why we end up with this terrible title, Manual of Biogenic House Sections, is that we needed to find a way that we were connecting to manual section, but it's actually a lie because it's a Manual of Biogenic and Geogenic House Sections, but that's an even worse title, so we didn't go there. No, instrumental in both of the books is the role of the section as a way for architects and design to think about things you don't necessarily see, but can understand in terms of how they perform, right? And to see that not as something that occurs after the fact. And again, I think that in the world of 3D modeling, Rhino, et cetera, we often model 3-dimensionally and the section comes after you're done in order to draw the section, to demonstrate, oh, look, I did a section. But our argument is that actually the section as a 2-dimensional cut can allow you to understand, and is a site for design, that you can kind of rework things in the section, in part because you're not doing everything simultaneously, and more importantly, you're not obsessed about the image of the building. You're interested in how it works, how it's organized, how structure flows, et cetera, right? So the section for us is instrumental in getting past image, in foregrounding performance, but the drawing type of the section perspective allows the inhabitation of the perspective to then gel with the abstract cut, so you get the visible and the invisible together, which is why for us it's always been so useful as a drawing type. Yeah, I think that the other thing that section allows us to do is just see things that you don't otherwise see, like insulation, right? Or assemblies of walls. And again, there's very little insulation in most renderings for obvious reasons, right? But I think as you start to see the thickness is not something that you could ignore or just the plan extruded up, but as a site of invention, then that becomes even more useful to use the section as the technique for getting at that. So.
Did someone else have? I don't need the microphone. I'm right here.
It's for the online.
Oh, right. So I guess this returns to the point you made early on about these are mostly looking at sections of houses and not necessarily housing.
Mm-hmm.
And I understand that was like a scale thing too, which helps with like demonstrating what is relevant in this case. I guess just for you and your perspective from like doing all of these drawings and everything, how do you imagine that these same principles might apply on that housing scale or even an urban infrastructural scale?
Yeah, it changes, but I think that's where, how do I put it? one of the criteria behind the selection of the houses in the book is that they needed to work with plant-based or earth-based materials in an inventive way, and they had to be spatially interesting, right? I think that still holds true when you scale up, right? So, in other words, what we found compelling about these houses is that they weren't just saying, okay, we're going to do a particular, interesting form. We're now just going to swap out the studs and the drywall with bamboo, right? It wasn't just a like to like, and then, they had a kind of spatial consequence. I would argue at the larger scale, that can become even more interesting, right? And to try to figure out where that goes. One of the tricky things, though, is, again, based on the products and materials out there, what happens when you move beyond a single story. I mean, straw, it's harder to do because of the compression, and so but I would argue that where things are going to be most interesting is where, frankly, a different paradigm of materials start to work their way into as many and affect as many different building types as possible. And the house may be just the initial experiment. The most interesting buildings, of course, are probably not going to be houses, right? Because they're going to be big scale, they're going to be urban, it's all the points you made. And it's starting to happen, which is good, but it needs to happen more quickly. And I don't know where it's going to go, but hopefully it'll be intriguing. So.
So you mentioned that sometimes you find yourself losing clients or like projects because of this wanting to do things in a more environmental way. So what do you find yourself more like clients that are interested, that come in with this interest of becoming more environmentally friendly, or the fact that you have to introduce this form of designing and educate them?
Yeah, I think that one of the things that is very encouraging is the number of institutions that argue we're not going to use fossil fuels, right? And so going to use geosolar, going to use solar panels. That's much more common, right? I think trying to make the argument that, look, fossil fuels are in our buildings in other ways, not just in the energy we produce, but in the actual building. That concrete takes a certain amount of fossil fuels for it to come into being, right? In addition to the greenhouse gases that are being released in its chemical processes. So I think being able to link these together and say, look, it's not, you can't just deal with fossil fuels from the energy consumption side. You have to deal with fossil fuels at the level of the building materials you're using, and then tie those together. The great benefit of, frankly, many of these plant and earth-based materials is they also don't have the health consequences. And I think I haven't been emphasizing that, but organizations like the Parsons Healthy Building Materials makes it very clear that we're living in a world where we're basically producing toxic environments, not just for the buildings themselves, but also where the materials are made, their end of life, et cetera. And so you get a double benefit of reducing or trying to eliminate as much as possible fossil fuels in all of its form, and a more regenerative way of living and way of producing materials, inhabiting with those materials, and then at the end of the life, what happens with them can be beneficial and not just form more landfills. So, but that's the easy part. The harder part is is it going to cost more? Is this approved by code? Our contractor is going to build this. Is this familiar? Can we be on time and on budget? That's harder, and it's very hard to say, absolutely, no question, here's 5 examples where I can prove it. So that's the hurdle. I think that's why it's going to take time and more demand, hopefully, to be able to accelerate the way these materials exist within the industry. So.
Do you find resistance with like contractors and people assembling these types of buildings?
I think anytime something is a variation to the known model, the answer is yeah. I mean, the usual reaction to straw bale construction is it's going to burn, right? It's straw, 3 little pigs, we know it burns, right? when it's dense enough, it chars, right? Just like mass timber. So I think that idea that, and then if you take the other insulation materials, XPS, EPS, and you put a small butane torch to that, they go up like you wouldn't believe. So I think any change is difficult. It takes time to be absorbed. So and look, one of the reasons for us being involved in working with straws, we needed to have we needed more knowledge in our own sense of how to make this work. And again, these are these are experiments that need to take place in multiple different arenas. So in order for familiarity not to be more prevalent. So.
Thank you.
Thank you very much.
Thank you. So I know many of you have class, both faculty and students. We may have a couple of spots if anyone is free to join for lunch. And then if anyone is available this evening for dinner at the Affleck House, please talk to Sarah and we can coordinate that. There'll be other opportunities in the future if we can't have everyone there today. Thanks for joining.